All right, so our last topic here to talk about is a discussion on the running time of Dijkstra's algorithm. So let me just put a pause here in the video so you can take a look at the code and make a guess at what the running time is. All right, well, let's key on two things here. We have two loops. Well, we have three loops. We have this while loop, this for loop, and this for loop. So how many times does this outer while loop iterate? Well, the outermost loop, the while loop, is dependent upon this condition here. And it starts out, found.length starts out at 1. And we're comparing that to n. And in each iteration, we add 1 to that length. So it's going to iterate n minus 1 times, which we can just say is big O of n times. All right, well, how about the inner two loops? It actually, like we've done in the past, we're going to basically look at both of these loops together. So one of them loops over vertices, another one loops over edges. How many times do the inner two loops run combined? I think the most intuitive way to look at these two loops are that we're looping over vertices here, but then we're immediately using those vertices here. We're looping over the edges connected to that vertex. So really, you could think of these two loops as iterating over all m edges ordered by vertex. So about halfway into this algorithm, we're going to have about half the vertices in V, which means if on average we have about half the edges, we're going to be looking at m over 2 edges, sort of in these inner two loops. At the very beginning, it's true that we're only looking at a couple edges, but then by the very last iteration, we might be looking at sort of the vast majority of all edges, because we have to loop over all vertices, and we're looking at all edges connected to each vertex. So it really benefits to, or it's advantageous to sort of take those two loops combined and say that really it's just looping over all edges, but doing so in a specific order, so ordered by the vertices themselves, which would give us a total running time of big O of n times m. And we'll find that we can reduce this. And we'll take a look at ways to reduce this when we talk about heaps in the next few lectures.